With that fan on?
Yeah.
Can you hear all right, Dirk? No, they tried that. Okay, I'd like to welcome you all to the fourth meeting in the Special Interest Earth Science Seminar. The topic this week is high-resolution seismic reflection and its application in Australia. And the session this week will, in fact, include three speakers. One is Reginald Nelson from the South Australian Department of Mines, who will speak first. You'll speak second. And the second speaker will be Phil Harmon from BHP's Coal Exploration Group in Brisbane. And third will be David King from the Department of Geology and Geophysics at University of Sydney. And without any further ado, I think we'll ask Reg to speak.
Thanks, Peter. We thought, as this is the state-of-the-art expose, we would perhaps not discuss principles, but leave them to the discussion period if anyone's interested. I'll be talking about seismic reflection experiments in pre-Cambrian areas, Proterozoic sediments, and with extensions and ideas on how you go about this in igneous and metamorphic terrain. And I'll be talking about the velocity and density structure of shallow crustal regions. One thing anyone who starts to dabble in this sort of thing finds is that you tend to wear a label. I guess it's the unspeakable in pursuit of the unattainable, if you forgive the paraphrase. And indeed, I've had people come in and thump the desk and insist that you only get low frequency reflections from basement. And you've got to use large offsets to do this. My first answer to that is, what is basement? And my second is, you've got to tailor offsets according to the problem, and there's always a compromise inevitable. You have to consider things like spatial aliasing problems if you're dealing with migration and velocity filtering. The steepest dip in an area defines the required relation between horizontal and vertical resolution. You also have to consider the coherence distance between detectors. This follows from Mac, 1974 geophysics, I think, and also from Levin. The coherence distance between two detectors is the distance at which they still give a reasonably coherent response. If they're separated, the noise from scatterers in the section means that the two signals at each detector are not very similar. And Levin defined the coherence distance from about 0.3 to 0.4 of a wavelength of the predominant coherent noise. High-resolution surveys have wide spectral bands of reflection energy, but the signal quality is often unacceptable because of random and organised noise. The frequent complexity of Precambrian structure and outcrop has led many to suppose that seismic reflection work is futile. And in the past 10 years, field mapping of exposed Precambrian crust in many parts of the world has shown that structures from often tens of metres to many kilometres in size are frequently simple in appearance. For example, Archean metamorphic rocks have large-scale layering often. Gneisses making up the layers are themselves banded. The layers are distinguished by major changes in composition, and this compositional variation implies sharp velocity and density changes. Finney, in 1979 geophysics, gives an example, a gneiss of granodiorite composition with a compressional velocity of 6 kilometres per second in contact with an amphibolite of 6.9 kilometres per second gives a reflection coefficient of about 0.07. This should be recognisable. It's often characteristic in well-indurated Precambrian sediments or metamorphic igneous rocks to see this alternation of high and low velocity, with the average velocity only slightly transitional with depth. Hence, the presence of a large number of reflectors does not imply a large increase in velocity. It can be said that the general processes controlling the average velocity structure of crust have acted uniformly over often wide areas. Canadian evidence shows a fairly rapid increase from approximately 5.5 to 6.1 kilometres per second in the top 1 to 2 kilometres of bedrock where it outcrops. Granitic areas are remarkably close to the velocity versus depth curve of Birch in 1958 for average granite. The increase is almost certainly caused by the closing of microfractures as a result of increasing pressure with depth. I'll just move to the overhead projector, I think. This shows typically how the effect of poor pressure on compressional velocity increases with velocity with confining pressure. Significant effects appear even if the crack porosity, microcrack porosity, is 0.1% or of that order. Anderson and others, 1974, have shown theoretically that planar cracks are much more effective in changing the elastic constants than spherical pore spheres. What I'm asking you to accept is that the average velocity in the shallow crust can vary from 5.5 to 7 kilometers per second, and that to low frequencies it appears as a mildly transitional zone with perhaps an increased gradient in velocity versus density as you go from Precambrian sediments to igneous or metamorphic rocks. And also to accept that we have laminated zones within this of alternately higher and lower velocities. These are superimposed on the smooth average velocity curve. I'd like you also to consider the relationship between velocity and density, because in dealing with reflection coefficients, we are dealing with velocity and density. Valarovich and others, 1967, produced a relationship for a pressure of 1 kilobar. Compressional velocity is 2.72 multiplied by the density minus 1235 meters per second. Here's a plot of various rock types. I've plotted them as a function of velocity, which in this case goes from 5 kilometers per second here, it's been rubbed out on this projection, to 8 kilometers up there. And I previously had the rock type superimposed. I'm sorry I didn't manage to get a slide back of this in time. This gives a reasonable sort of estimate of velocity versus density for crustal type rocks. Where ore bodies are concerned, I think there's significant evidence that the mean atomic weight plays a part. Typically in a lead zinc body, you may have a compressional velocity of, say, 6 kilometers per second, perhaps even less, but the density may go up to 5 grams per cc. So that when you're dealing with ore bodies, densities may play a significant part. There's abundant evidence for lamination such as I've described in the deep crust. Fuchs, 1969, is a good reference. Other workers, such as Smithson, have examined effects in the shallow crust. Here's a typical field record produced by Scott Smithson, showing a very nice reflector down here, in this case at a time of 2 seconds to a reflection time. The effect of these laminations is to tune reflections. A reflector composed of a series of thin layers of alternately higher and lower velocity will produce a composite reflection. I may have to slide this around a bit, or perhaps that'll do. This refers more to the deep crust. What we have here is the velocity variations, various layers of different thickness. Here we have interlaid granite and gabbro, with a fairly moderate reflection coefficient, but producing, for different frequencies, a very large tuning pulse. This reflected pulse is affected in amplitude, bandwidth, and apparent arrival time, and it depends on the number of laminations as well as the reflection coefficient and the thickness. And the angle of incidence is another very important factor. I believe this tuning effect is a very important factor in hard rock work. In fact, Hajnal, 1979, has shown from synthetic seismograms based on sonic logs that you need frequencies of at least 100 hertz for shallow mapping, so down to a depth of 1 kilometre. And certainly from our work on the Stuart Shelf, I'd agree with that. So this is a good point to define what I mean by high resolution in this context. We are looking at peak frequencies of at least 100 cycles and preferably higher, say at least 200 cycles. And our aims are to trace intrabasement horizons to see if certain features can be used to distinguish one zone from another. These features might be the length, dip, spatial density of reflectors, or the presence of diffractions. Even transparent zones may imply relatively homogeneous igneous intrusions. We are going to try to apply this to search for mineral deposits associated with certain structural features of basement, such as major faults or intrusions. And possibly, we'd hope, even to detect ore bodies directly because of the high density contrasts. I noted in the session the other day on complex resistivity that the Allura deposit has, I believe, fairly uniform velocities in comparison to country rock, but a very great density increase. And to summarize again, the factors affecting the velocity structure of the crust are: one, the tectonic style of the region, the geochemistry of the rocks, and its orogenic history. Two, the distribution of water in the crust, either chemically combined to give hydrated minerals or free as pore fluid. Three, the past and present state of the stress field and presence of microfractures. And four, the past and present temperature regime. And again, with respect to crustal features, we note one, large-scale banding or layering in metamorphic and Proterozoic sedimentary rocks. Two, often intense folding of these layered bodies. Three, presence or otherwise of faulting. Four, presence of igneous intrusions. And the fact that folded metamorphic rocks often have stratigraphic and structural dimensions from tens of meters or less to several kilometers, and impedance contrasts of up to 20% between layers. I think at this stage I may go into the slides and perhaps ramble my way through them. It's rather informal, I think, from here on. Perhaps I can sit down. This is an example of a banded iron formation, just to show the scale of some of the bandings. The next slide is shows it again on a slightly larger scale, and so on and so forth. You can get up to quite large scale banding in these environments. These are typical densities sampled at 1 meter intervals on core from the Stuart Shelf. We haven't as yet measured sonic velocities on core because of equipment problems, and also because I'm doubtful whether this is a valid measurement once you've removed the rock from the existing stress field. We also don't have sonic logs from these holes because they're very small diameter holes. But typically you can see a generally 5-meter thickness cyclic variation in many of the formations, and we'll probably see more of these later on. This is the classic Wadesh diagram. It shows the composite reflection from the top and bottom of, in this case, a 20,000 feet per second or 6,000 meters per second layer, surrounded by 10,000 feet per second or 3,000 meters per second material. And down the side there, the bed thickness goes from 1 wavelength down to 1/40th of a wavelength, and you can see the corresponding changes in the reflection character of the pulse, and in particular, around about 1/4 of a wavelength, the tuning effect of the interference between the two pulses that you can see interfere in the top right-hand corner of the slide. This can be expressed in another way. This slide shows the again, we're looking at the convolution of 2 Ricker wavelets, in this case 8 to 32 hertz with peak frequency of 19 hertz. The separation between them is defined by Tor. The apparent bed thickness is shown here against the actual bed thickness, and you can see that after a certain point the apparent thickness stays the same. At that point, which is called the tuning thickness, we have about 6 dB increase in amplitude of the reflected pulse. And remember, this is for a 32 hertz peak wave, and we talked about 5 meters bed thickness on, for example, the Stewart shelf, which is a bed thickness of, I think, about 2 milliseconds. So on this scale, 2 milliseconds is there. For a 30 hertz pulse, you're probably down about 20 dB. So such a layer would become increasingly transparent for lower frequencies. This is an example of an expanded spread shot on the Stewart shelf. It shows typically fairly high near-surface velocities and massive surface ground roll problems. Any reflections in there certainly aren't very evident on this particular display. After filtering this, with digital filtering, you can see certain evidence of some reflections in this particular zone. They're more pronounced because someone's gone over them with a pencil, but they are there and they're very hard to see. This implies that surface waves are at least 40 dB above any reflections in this area, and so this is a large problem. Notice also the frequencies we're dealing with: 80 hertz high cut, 35 hertz low cut. I've put this slide up to show the effect of burying charges, which is a fairly standard technique in high resolution work, and their effect on the surface waves. For frequencies of 10 hertz and 20 hertz, you can expect around about 24 dB attenuation if your charge is at 40 meters. And that's about the effect that a good surface array would have on these waves. But when you're dealing with the 100 to 200 hertz band, you can see that a depth of 10 to 15 meters will attenuate these very strongly, down around the 50 dB mark. It means that you've got to use low-cut filtering when you record, in many cases, to eliminate these surface waves. Here's an example. Various shots at the same depth, 26 meters, shot in a shale which is at the base of the weathered layer. This one here, field filters are 60 hertz low cut to 500 high cut. Here we have 250 hertz low cut, and again 500. And here we have 120 hertz low cut, and again 500. So I'll try to focus that a little bit. That's better. Reflections appear in the middle one, which is the 250 Hz low cut, as almost flat line bands across here. They are somewhat in evidence when you use 120 Hz low cut, but if you go to a 60 Hz low cut, it's very, very hard to see them. This is again expanded spread, shot with charges at depth, and the depths of various shot holes are given here, 14 meters, 9.8 down to 10 meters. The sample rate was 1/4 millisecond, and the low cut in this case was 250 Hertz low cut. And you can see reflectors with good move out across the record, and they correspond to the ones in the previous slide. Again, another display from the Stuart Shelf. You can see particular dolomitic bands within this dolomitic shale member showing quite peaky density values. And in the beta volcanic section here, the basalt flows show also significant velocity variation, density variations, with this massive trachytic flow here showing quite large density values. This was shot in the same area as the expanded spread. The drill hole was the one shown in the previous slide. It's over here to scale. This is a depth section, not a time section. It's been converted using velocities information from the hole. The hole is there on the section, and you can see these two little bands in particular correspond to these two reflectors here. The top of the volcanic formation correlates fairly well in here, and this massive trachytic flow in here. There's a change in character, which I've postulated as a different formation here, and another change in character down there. The overall dimensions are 610 meters this way, and a depth of about 1,200 meters down here. Right, this is just to refresh ourselves with the factors affecting seismic velocity: porosity, fluid content, temperature, pressure, grain size, cementation, direction with respect to bedding or foliation, and I think very importantly in hard rock work, mineralogical composition. And this slide simply says, with decreasing porosity, seismic velocities depend mainly on the elastic properties of the minerals making up the rock material itself. And again, to recap on some grain densities of common minerals, we have here a suite: gypsum 2.32, quartz 2.65, shale 2.6 to 2.65, calcite 2.71, and so on, dolomite and hydrite, magnetite, down to hematite with 5.27. And this, which is taken from Dobrin's book, it also includes Birch's information at a pressure of 1 kilobar. Shows the relationship between velocity and density. And I'd suggest that for some ore minerals with different mean atomic weight, we may be looking at higher densities, but velocities in this perhaps 6 to 7 kilometer per second range. Some of the sample examples I'll be showing now are from the Stuart Shelf, which is an area we have been working in extensively. For those of you who aren't familiar with it, it's in South Australia. It abuts the Adelaide geosyncline. This is a generalised section across it. Dips are generally fairly gentle, which is very good from our point of view. There's a history of block faulting. There was a hinge zone in here. You have the Mount Gonson copper mine located about that stratigraphic position there. In the same area, we have the Olympic Dam copper uranium ore body in a slightly different stratigraphic setting. I think the important features are perhaps the Pandara Formation. We've shot extensively an outcropping Pandara Formation. The beta volcanics you've seen on some of the previous slides, and the Tapley Hill Formation also. This expanded spread was shot on outcropping Pandara Formation. After that I shall focus it. Okay, we're looking at a variety of reflectors. The display doesn't do them justice, I think, but there are many up in this region. There's quite a strong one at around 0.7 seconds. I'll just focus in on this zone in here. And you may be able to see it a little bit better, just going through there. This line was shot to give a CDP stack of approximately 14-fold. And I've shown a set of constant velocity stacks, which will show the 0.7 second reflector, which is at this level, stacking in best at around 5,300 meters per second, which is a good average velocity for that region, or good RMS velocity, I should say. And this is in the same area. We have a drill hole on this line, or actually just off it. We have a gravity profile and magnetic profile. The drill hole went through Pandara Formation into volcanics, acid and basic, and metavolcanics, finishing in granite at a depth of about 1,000 meters. That is a squash plot. The section is about 4 kilometers long, so there's considerable vertical exaggeration. That would correspond to about 1,000 meters there. There's also a very deep-seated thing here, probably at about 3 kilometers depth, which certainly doesn't look like a multiple. The other interesting things are the shales, which the Pandara Formation is a sandstone, and it does have shale members near the base, and these were picked up very well by this drill hole. And I think we can correlate this granitic contact with the zone in here. There's another set of lines. The lines themselves were shot in this fashion. An initial experimental line was shot in here. This is an error mag anomaly. And we're looking at pretty well the whole Stewart shelf sequence, as I showed in the previous slide, in this zone. The mag features are interpreted to be from bodies at depths of about 3 kilometers. We'll be looking at this one first. This was an experimental line. It was 12-fold stack, 10-meter geophone spacing, and shot spacing, of course. The shots were at a depth of 15 meters. I can't quite remember the charge size. I think it was about 5 ounces. This is the result from the experimental line. That's a distance of about half a kilometer. That's probably a depth of 1,200 meters. Well, this gave us some heart, and we looked at expanding spreads in the area and thought, well, okay, we can increase our geophone spacing to 25 meters and reduce our costs of drilling shot holes. And these were typical field records from that next survey, which were the 2 cross lines over the Aeromag anomaly. And you can see quite good reflectors. These are just straight raw field records, unfiltered, as they come off the tapes. And these were the sections we produced from this area, about 2.5 kilometers that way. This is the northwest southeast cross line. These are magnetic values over each line. Interesting thing to note is that, as always, where you have a cross line, it's right over the zone of bad data. But it does show quite a lot of structure, a general regional dip towards that direction, and evidence of fairly complex faulting. Also, there do appear to be reflectors down below the shelf sequence dipping through there. Okay, that's really dealt with the Proterozoic sediments. I haven't any examples that I can show of complex terrain, but I've got a few models here we can perhaps look at, and it's interesting to look at this sort of model and wonder what the heck you get in the way of a seismic response from it. So we'll throw in a 200 Hertz Ricker wavelet. We have these velocities and density variations. The ore zone is 6.1, 2.7, not a very great increase, but we do have significant acoustic impedance contrasts. And it's a very crude approach, but what was done in this case was to generate reflection coefficients at the boundaries and virtually demigrate that section after convolving it with a wavelet. And this is the sort of reflection response you'd expect to see from that sort of terrain. These models, incidentally, are due to Scott Smithson of the University of Wyoming. Here's another model, chevron folding, the granite batholith. You can see the transparent zone from the granite batholith and the various diffraction effects from these tight folds. Input wavelet was 100 Hertz. Horizontal distance for comparison is 1 kilometer that way, and vertical distance is 1,000, 2,000 meters that way. As a final example, we have this deep-seated crustal feature in the Archean in Greenland, I think is the model that it came from, showing a country rock velocity of 6.2 kilometers per second, a density of 2.7, and in this zone here, 7.2 kilometers per second and 3.1. And again, that's the sort of model you'd expect. Well, perhaps I'll just use the overhead projector briefly. Once you start dealing with steep dips and layered, especially high velocity encased in low velocity media, you run into problems associated with CDP stacking. Number one, because of the large dips, reflections added by the CDP stacking method don't represent identical areas of the dipping bed. Two, with steep dips, the horizontal displacement of reflections which occurs in migration may be as large as the reflected depth, so again the CDP and stack is inadequate. The angles of reflection differ for anisotropic and isotropic media. Noticeable differences occur at critical angles, so again that's a problem where you have steep dips. You probably find that the CDP data stack with a mixture of vertical time-weighted horizontal velocities. CDP gathers under these conditions are not even an approximate sample of a single wave field where you have this elliptical velocity dependence or lateral inhomogeneities over the cable spread. The inhomogeneities and interface curvature can lead to a multiplicity of reflections, reflected ray paths, and also mode conversions. This can cause kinematic and dynamic properties of the elastic waves to become complex. And possibly more important than any of these, a reflector comprised of a series of thin layers of alternately higher and lower velocities will produce a composite reflected pulse whose amplitude, bandwidth, and apparent arrival time will change as the reflecting angle changes, or as the incident angle changes. As a result of this, and because of mode conversions and variations in the reflection coefficient, the interference pattern generated is highly sensitive to the angle of incidence. That means with changing angles of incidence, you have gross variations in the waveform, and this can also decode the CDP stack. The assumption of waveform invariance with source-receiver offset may be grossly in error in certain cyclical bedding or laminated environments. As a corollary, though, this variation of waveforms may be a useful measure and may give some information about the layering. I guess the message from this is once we are dealing with steep dips, we should question whether a CDP stack is adequate, and perhaps look at some of the techniques that are now being used in the CoCorp data, Finney's imaging process, or Schultz and Clarebow's slant stacking processes, more in the common offset domain, I guess. And I didn't really talk about this slide, but it shows a model of various velocity variations of a thin laminae, and here we have change in angle of incidence and the resultant waveform composite. Thank you. I guess I'll pass over now. Well, perhaps I'll answer questions if people wish to ask them.
You have questions? Would you
Sorry.
use the microphone?
Reg, you're talking about the density and variation of rocks and the mineral composition. It's not really sufficient to just talk about the mineral composition. You have to talk about the distribution of that mineral composition, don't
Sure,
you? Because a couple of percent of hematite can up the density of a rock by quite a lot.
Yeah.
Did you, when you went overseas, talk to people about that phenomenon and get any gut feeling for where what constitutes a reflector in terms of density variation?
No, I haven't really got that pinned down yet. It's a suspicion, I guess, more than anything else at this stage. But it's certainly an area that warrants investigation.
Yeah, if you see, in normal oil work, your porosity is really what provides your velocity
You're looking
change.
at the time average equation, and
Yeah,
porosity
where
plays a major
your grains actually play a more important part in Proterozoic type rock.
I've got one. We'll be looking for some test areas on the Stewart Shelf first half of next year. Are those areas where the actual sections were shown? Would those be available for?
It would depend on the companies concerned, I think. I think companies concerned would be very receptive to work done in their areas.
Provided they got all the data, yes. I understand.
Yeah, I don't think you'll find an area on the Stewart Shelf that hasn't got an exploration license slapped on it at this stage.
Any more seismic type questions? Okay, well, perhaps you'd join with me in thanking